So same. Principle of launching an artificial satellite. So how we are launching the satellites actually, that we are going to study. Okay ma? See ma. Consider here there is one satellite revolving around Earth. Okay ma? It is revolving around Earth. Now this satellite requires how much energy for rotation? Can you say anybody? For this satellite to rotate, how much energy is required? Huh? How much energy is required? We are making satellites to rotate around Earth, no ma? How much energy we have to supply? Energy of satellite already we have studied, no? What is the formula for potential energy of a satellite? Minus gmm by r. What is the energy for kinetic energy of a satellite? Gmm by 2r. That's what we have studied, no? Total energy minus gmm by 2r. So if I supply that much energy, that is enough, no? Sima. So energy required for rotation of satellite is how much? It is 0. No need of any energy. 1 liter petrol gaani koncham sunrise gaani emi avasaram ledhu. Okay ma? Why energy is not required? Because satellite is a freely falling body. What kind of body ma? It is a freely falling body. See ma, if I release this pen, it will touch ground, no? And for touching this ground, to this pen to go and touch the ground, is any energy required? No need of supplying energy. Automatically gravitational force will pull this pen and pen will fall down. Same concept is happening with the case of satellites also. Say for throwing it is necessary, for launching it is necessary. For what I am writing here, for rotation it is not required. Yala anedi ikkada chuddam chudanma. So what I do is I go to a particular height. So first satellite will be taken to a particular height, no ma? Through rockets. Launching rockets will be there, no? Through rockets, first satellite is lifted to a particular height. From there what I will do, if I give a very small velocity, then it will fall somewhere here. That's all, no? Okay ma? If a small horizontal velocity is given, it will fall here. And if I increase the velocity, then it will go and fall somewhere here. Okay ma? But if I give suitable velocity, then also it will try to fall down. But there is no earth here. Earth is in the form of a sphere, no ma? So satellite is always trying to fall down. But it is not falling, because it is falling in the curvature of the earth. It is falling in a particular distance, at a particular radial distance from the surface of the earth. So satellite is what kind of body? Always a freely falling body. Okay ma? And freely falling body doesn't require any energy. So that is why it is continuously trying to fall on the surface of the earth. Satellite ఏమరా చేస్తుందంటే రొటేట్ అవ్వటం లేదు, అది అర్త్ దొరికితే కింద పడిపోదామని ఉందన్నమాట. ఓకే మా? So it is trying to find the surface of the earth, but unfortunately it is not able to find the surface of the earth. One more method of explanation is we can say like this. Sima, if I give some tangential velocity, this is the direction of tangential speed, no ma? Body is always trying to move in a straight line. I can say like this also. Okay ma? Any body naturally always tries to move in a straight line, no? Body cannot change the direction unless you apply force. Every body continues to travel in the same direction according to Newton's first law. Clear? So body is trying to move in a straight line. Satellite is trying to move in a straight line. But the gravitational force of earth, that is providing centripetal force to this satellite. Because of this centripetal force, it is moving in a circular path. That is the second explanation. Both are correct. Are you able to understand what is happening? First explanation is it is trying to fall on the surface of the earth, but it is not able to fall down. Earth ఇప్పుడు దొరుకుతుంది పాపం ఎదురు చూస్తూ ఉంది. Earth ఎప్పటికీ దొరకదు దానికి. Clear? Because the shape of the earth is spherical and it is also falling in a spherical shape. Okay? One explanation is that. Another explanation is any body always try to move in a straight line. But if it should move in a circular path, centripetal force should be present. And that centripetal force is provided by gravitational force of earth. These are the two explanations. Okay, so based on that only we will derive orbital velocity. Based on this concept of centripetal force only, we derive orbital velocity. Understood, Nama? So write down. So what we write here? So if a suitable horizontal velocity, is given, okay, ma, then body falls continuously in the curvature of Earth. And it becomes an artificial satellite. Okay, ma? So every artificial satellite is a freely falling body. Is what kind of body, ma? It is a freely falling body. Okay, ma? And what is the weight of a freely falling body? 0. Freely falling body does not have any weight. Weight exists only if there is some opposing force. For example, I release this pen. Until it touches the ground, it is a freely falling body, no? What is its weight? No weight, it doesn't have any weight. Are you able to understand, no? So therefore, astronauts means the people in the satellite. Astronauts experience weightlessness. They experience weightlessness, no? Why? Because they are also freely falling. Okay, ma? They are freely falling doesn't mean that a force is not acting on them. Force is acting, that is why they are moving in a circular path, no? But this is what kind of movement? This is freely falling motion. So G value is not 0, but weight will become 0. So therefore you can say G value has become 0. Because any freely falling body does not have any weight. That's it. So that is the reason why people in the satellites, they will be flying, no, ma? Why they are flying? Because they are freely falling bodies. They are trying to fall on the surface of Earth. And freely falling bodies doesn't have any weight. That is why they are floating in the air. That is the reason. Okay? Okay, ma. So the next concept in gravitation is moment of satellites, ma. Okay. So first of all, we will study about orbital velocity or orbital speed. So what is meant by orbital velocity? See, my satellites, they will be revolving in a particular orbit, no? And depending upon the size of the orbit or radius of the orbit, satellite should have particular velocity. It should have particular speed. Okay, ma? When satellite is very close to the planet, then its tangential speed will be very large. Tangential speed, or you can call it as orbital velocity or orbital speed, anything. Okay, ma? But as the satellite is rotating in a greater orbit, therefore its velocity continuously reduces. Are you able to understand, ma? So we are trying to derive an equation for this orbital velocity or tangential velocity with which satellite should move in this circular path. Okay, ma? See, ma, how this satellite is able to move in a circular path? If satellite should move in a circular path, what is necessary? Centripetal force is necessary. Clear, no, ma? So can I say that centripetal force is provided by gravitational force? That's all, no? What is the formula for centripetal force? Centripetal force should act on this small m, no? So mass is m, velocity is v square divided by, and from the center, what is the distance of this mass? It is r, small r, mv square by r. Okay, ma? So this is equals to gravitational force. Now what is the gravitational force of attraction between two masses? Newton's law of gravitation we have now, F G capital M into small m divided by r square. This is the relation which we have. That's all. So therefore one r and one square will get cancelled. So small m and small m also will get cancelled. So therefore v square is equals to, so G capital M divided by R. So therefore V is equals to square root of G capital M divided by R. And this V itself is called as tangential speed, or I can call it as orbital velocity also. Okay, ma? So for this radius, this should be the amount of orbital velocity. So here one point which I can say is that G is a constant, you know, ma? Universal gravitational constant, it is a constant. And what about M? M is mass of the planet, no? Mass of Earth is a constant. So M is also a constant. Clear? Then orbital velocity is inversely proportional to root of R. Clear? That's what I can write now. So what do you understand? Now what we understand is that if radius increases, velocity should decrease. So when satellite is rotating at a very large distance, then it should be rotating very slowly, because they are inversely proportional to each other. And when satellite is very close to the Earth, then the speed of the satellite should be very large. Are you able to understand, ma? That's it. Make a note up to here. Okay. So therefore, for same planet and same satellite, or any satellite also you can call, okay, ma? Orbital velocity V01 by V02 is equals to root of R2 divided by R1. So I can write like this also. Okay. Now we will do some more calculation in this one. See, we know that orbital velocity V0 is equals to square root of Gm divided by R. Now, when body is very close, when satellite is very close to the planet, okay, very close means what? We know R value is equals to capital R plus H, no, ma? Small r is equals to, small r means what is meant by small r here, ma? Distance of the satellite from the center of the planet, that is called as small r. Okay. So small r can be written as capital R plus H also. When satellite is very close means what here? H is very less when compared to R. That is the meaning of this one. Okay, ma? This height which you are taking, it is very less when compared to radius of the Earth. For example, what is the radius of Earth? Radius of Earth is 6,400 kilometers, no, ma? So for small heights, for example, you take height is 100 kilometer, 200 kilometer, 300 kilometer, for such small heights, 400 kilometer, they are very small heights, no, ma? For such conditions you can write V0 is equals to square root of Gm divided by capital R only. Instead of R plus H, you can write R only, because H is a very small value, no? Are you able to understand? So this is one equation of orbital velocity for surface satellites. So what is meant by surface satellite, ma? Surface satellite means satellite which is very close to the surface of Earth. For example, communication satellites, they are surface satellites. India also given has many communication satellites, no, there will be at a very small height. Very small height ante cheyi pettukonandukochani kaadu. Some 200, 300 kilometers height. When compared to radius, that height will be very small. Such satellites are called as surface satellites. Okay. So for bigger heights, this relation you can use, ma. Square root of G capital M divided by R plus H. Okay. And when a satellite is very close to the surface of Earth, this equation directly you can use. Okay. Make a note. Now see, ma. So therefore, for surface satellites, what is the equation of orbital velocity? V0 is equals to square root of Gm divided by R. This is the relation. Okay. Now here equation is in terms of capital G, no? I can write this equation in terms of small g also. How we can write? See, we know that G is equals to Gm divided by R square. This relation we know, no? Therefore Gm will be how much? Gm will be equal to Gr square. So instead of Gm, you substitute this Gr square. Therefore orbital velocity is equals to square root of gr square divided by r. So r and square get cancelled, so root gr. So therefore orbital velocity is equals to square root of g into r. This is the equation. Understood now? So, and this equation is also satisfied for only surface satellites only. For any other satellites at a greater height, this is the equation which you have to use. Square root of gm by r plus h. Understood now? Make a note. Okay. So, for example, if I take a surface satellite, so V0 is equals to square root of capital G value is how much? 6.67 into 10 power minus 11. Mass of Earth is how much? 6 into 10 power 24 kg. Divided by radius of Earth is 6400 into 10 power 3 meters. Okay. So if I do this calculation, that is for surface satellite, the speed will be approximately 8.1 kilometer per second. Approximately. Okay, ma? It means the satellites which are very close to the surface of Earth, they will have how much speed? They will have a speed of 8 kilometers in 1 second. Okay, they should travel 8 kilometers in 1 second. Communication satellites, the satellites which are very close to the surface of Earth. Understood, no? Okay, ma? So this is for which satellite? For surface satellite. Okay. Then we study about time period. What is meant by time period? Time period means what? Time taken for one rotation around Earth or any planet. That is called as time period. Clear now? So how can I calculate time period? Time is nothing but distance divided by speed. I can write like this, no? Total distance of the circular path divided by speed, or you can say total circumference of the circular path divided by speed of the satellite. So distance I can write 2 pi into r. If radius of the planet is radius of the satellite at which it is rotating, if it is r, 2 pi r divided by speed is nothing but orbital velocity or orbital speed. Understood, no? So V0 value already we have calculated, no? This one, substitute here. So therefore T is equals to 2 pi small r divided by V0. V0 I can write it as square root of Gm divided by r. Okay. So if I do small manipulation, then I can write the square root of r divided by root of Gm. I can write like this also. Okay. Understood, Nama, what is happening? Then this r I can take inside this brackets, no? Then it will become r square. So r square plus 1 r power cube, r cube it will become. So therefore time period I can write it as a 2 pi into square root of r cube divided by g into m. R power 1 only. Root r means r power 1. It is present inside the roots only. We are not taking it outside. This one I am taking inside. R if it goes inside the root, it will become square number r square. R square plus 1 r cube. Clear? Same equation I can write like this also. So 2 pi into square root of r plus h whole cube divided by gm. So this is the different methods of calculating the time period of oscillation. Time period of rotation. Are you able to understand? Clear, ma? So same equation how can I write for surface satellites? For surface satellite. Okay, ma? Surface satellite means h is very less when compared to r, no? Clear, no? So therefore instead of r plus h, just I can write r only for surface satellites. Therefore it is t is equals to 2 pi square root of r cube divided by g into m. I can write like this. అర్థమవుతుందా ఎలా చేస్తున్నాము? ఓకే మా. Then again instead of gm I can write gr square, no? Instead of gm I can write gr square according to this one. So substitute that. So therefore t is equals to 2 pi into square root of r cube divided by gr square. Okay, ma? So r square and cube get cancelled. So t is equals to 2 pi root r by g. Okay. So I can write it like this also for surface satellites. Are you able to understand? That's it. Okay. Now let us see one more equation na? For same time period. So we have the equation t is equals to 2 pi into square root of r plus h whole cube divided by gm. This is the equation which we have now. So sometimes questions will be given on mass and density and radius of the planet also. He will give questions on mass, he may give questions on radius of the planet, he may give questions on density of the planet also. Okay. Then in that condition what I can do, we know that density is equals to mass by volume, no ma? Therefore what is mass? Mass is equal to density into volume. So density into volume of a sphere. Planet is a sphere only, no? Solid sphere. What is the formula for volume of a sphere? 4 by 3 pi capital R cube. That's all, no? So take this value and substitute here. Clear? Therefore t is equals to 2 pi into square root of r plus capital R. Capital R plus h whole cube divided by g into m. Instead of m, I can write rho into 4 by 3 pi capital R cube. So I can write like this also. Are you able to understand, ma? So this is one method of calculating the time period. If question is given on density. Density of a particular planet is this much. Then what will be the time period of oscillation of a satellite? Then this equation you can use. Just instead of mass, I am writing density into volume. That's all. Are you able to understand, ma? Now again you write the case. Case is for surface satellite. For surface satellite. Okay, ma? What is meant by surface satellite? H is much less than R. In that condition you can neglect this H value. Okay. So therefore, let us see the equation. Therefore t is equals to 2 pi into square root of r cube divided by g into rho into 4 by 3 pi r cube. Okay, ma? So r cube and r cube get cancelled. So therefore t is equals to 2 pi into square root of 3 divided by 4 pi rho into g. Okay, ma? This is the equation of time period. And calculation ekkado teda kodta unnai. Okay, ma? So therefore I can simplify this one, ma. Square root of this 2 pi, if I take inside, it will become 4 pi square, no? 4 pi square multiplied by 3 divided by 4 pi into rho into g. Okay. So 4 and 4 square and pi will get cancelled. So therefore t is equals to square root of 3 pi divided by rho into g. So this is one more equation to calculate time period in terms of density of the planet. Rho means density, no ma? So in terms of density, this is one more equation I can write. Clear? And some more equations you can write. See, ma, here instead of gm again you can substitute gr square. No? Instead of gm you can write small gr square also. Then you will get one more equation. Okay. So whatever it may be, basic equation is only one equation. Now what is the basic equation? Time period is equals to 2 pi r divided by orbital velocity. This is the basic equation. From this equation you can go on deriving any number of equations. Are you able to understand? Some equations on small g, some equations on capital G. Any number of equations you can write down. Understood, no? So here also this 4 pi if you take inside, then you will get another equation. Arthamatunnayi kada equations? That's it. Okay, ma. So after calculating different equations of time period, we can study equations of angular momentum of a satellite also. Okay, ma. So angular momentum of a satellite. So angular momentum formula mvr, no ma? One formula of angular momentum is I into omega. In rotational dynamics we have studied. One more equation is mvr. Okay. And what is meant by v here? V is nothing but orbital velocity. So substitute orbital velocity. So m into v. Instead of v, I can write a square root of gm divided by r multiplied by r. When satellite is rotating at which radius? At a radius of r. R is nothing but radius, no ma? And it is also called as capital R plus small h. Understood, no? So therefore, L is equals to m into root of gm into r. Correct? And this is not capital M, this is small m. Because small m is the mass of satellite, no? So m into square root of gm into, here I have one r, no? This r I can write it as root r into root r. One root r, another root r get cancelled, then this is the equation which I will get. Okay? So this is the equation to calculate angular momentum of a satellite. Or just you can remember this equation, mvr. Instead of v naught, you substitute orbital velocity, then I will get the answer. Omega. Angular momentum, two equations are there, Nama. One equation is mvr, another equation is I into omega. Anyone you can use. Where? That angular velocity ka subaka. L ante angular momentum. Okay, ma? So next concept which we are studying is energy of a satellite. Okay? See, by any satellite which is revolving around this planet, okay, ma? It will have two energies, no? Can you say what are the two energies it will have? Because of velocity, it will have kinetic energy. Clear, no? And these are two masses separated by a distance r, no? Ma? If two masses are present at a distance of r, then the gravitational potential energy also will be present. No? Already we studied in the last class, no? Ma? To place two masses at one distance, we have to do some work. And that work done is nothing but gravitational potential energy. Okay? So therefore this satellite will have two energies. One is kinetic energy because of rotation. Another one is potential energy because of its position. Are you able to understand? So right now. So any satellite will have two energies. Okay? So first one is kinetic energy due to rotation or due to velocity. Which velocity? Orbital velocity. Okay, ma? So kinetic energy formula half mv square, no? And what is meant by v? V is nothing but orbital velocity. So substitute. So half into m into square root of g capital M divided by r whole square. Clear, no? So therefore what is the equation of kinetic energy? So g capital M into small m divided by 2 into r. This is the relation. Understood now how we are getting? So half m instead of v, just I am writing the equation of orbital velocity and I am getting the equation. That is the equation of kinetic energy when satellite is rotating at a height of r from the center of the earth. Okay. Now satellite has one more energy, Nama, potential energy. Potential energy because of position. Okay. Now when two charges, when they are separated by small distance, m1 and m2, when they are separated by distance of r, then what is the gravitational potential energy? It is minus g m1 m2 divided by r. This was the equation which we have studied previously, no? Yesterday only we studied gravitational potential energy, no? How many pairs are there? Only one pair is there. So only one term of gravitational potential energy. Minus g m1 m2 divided by r. So here also earth is one point mass where mass is totally concentrated at its center, and this is another point mass. Understood, no? Okay. వీళ్ళు మాట్లాడుతున్నారా చదువుతున్నారా వీళ్ళు? ఉమేష్ వాళ్ళని పిలిచిరా పోసారి. Okay, ma? So therefore now substitute the values, ma. So gravitational potential energy is equals to minus g. One body is mass, no? A mass of earth, no, ma? Another body is mass of satellite divided by r. This is the equation for gravitational potential energy. Understood, no? So therefore, sum of kinetic energy and potential energy is called what? What? Mechanical energy. Sum of kinetic energy and potential energy is nothing but mechanical energy. So total mechanical energy is how much? Total mechanical energy. Just you can write total energy is equals to sum of kinetic energy plus potential energy. Okay. So what is the kinetic energy I got? Kinetic energy is equals to G capital M into small m divided by 2R. And what is the potential energy? Minus G capital M into small m divided by R. So if you subtract them, I will get minus G m divided by 2R. That is the equation for total energy. Understood, Nama? So therefore, what is the equation for total energy? Total energy is equals to minus G small m into capital M divided by 2R. This is the relation. Understood, no? Clear, ma? Now, we have to write relations between these energy concepts. So before that, I will study binding energy. Binding energy. Okay. Now, can you say what is meant by binding energy? Total energy I have calculated, no? Total energy. How much is the total energy? Minus G small m into capital M divided by 2R. Now here I got negative symbol. What does negative symbol represent? What does negative symbol represent? In chemistry also we have studied, no? Energy of electron in Rutherford's model as well as Niels Bohr model. There also same concept we have studied. Clear, Nama? What is meant by negative total energy? Total energy I got negative, no? What is meant by negative energy? Negative energy represents that this particular satellite, it is bound to the gravitational force of that particular planet. Okay, ma? It means it has to compulsorily rotate in that orbit, or it is present under the effect of gravitational force of the planet. Okay, ma? Now if I give same amount of positive energy, then what will happen? If I give same amount of positive energy, then what will happen? Then total energy will become 0. That's all, no? For example, if it is minus 10 joules, I will give plus 10 joules. Then minus 10 and plus 10, 0. Then what is meant by 0 energy? 0 energy indicates that that satellite is no longer under the effect of that planet. It permanently moves out of the gravitational field of the planet. That is called as total energy. Total energy becoming 0. Okay, ma? And that exactly positive energy is called as binding energy. Okay, ma? So therefore, how I write binding energy? Binding energy is nothing but a negative of total energy. Okay. So negative of, what is the total energy? Minus Gmm divided by 2R. So therefore, binding energy is how much, ma? It is Gmm divided by 2R. This is the relation. Okay. So what is the meaning of binding energy? The amount of energy supplied, to the satellite such that amount of minimum energy, you write, and that is better, amount of minimum energy such that it permanently just escapes the gravitational field of planet. That much amount of energy is called as binding energy. Okay, ma? So because of this much energy, it is rotating around the planet. Okay, and what is meant by negative value? Let us write here. Okay. So total energy is how much? Total energy is minus Gmm divided by 2R. Okay, ma? So total energy is negative. Okay. Negative total energy represents attraction. What does negative total energy represents, ma? It represents attraction. That is, satellite is under the attractive force of planet. Okay, ma? if total energy becomes 0, if total energy becomes 0, if total energy becomes 0, then the kinetic energy of satellite will be how much? Kinetic energy of satellite will be 0, and potential energy of satellite also will be how much? Potential energy of satellite also will be 0. That is satellite is no longer under the effect of planet. Okay, ma? Therefore, what is the minimum amount of energy I have to supply, ma, so that it escapes the gravitational field? Minimum amount of energy is equal amount of positive energy equal to the total energy. Understood, no? If I supply this much amount of positive energy, then total energy will become 0. Are you able to understand? Then the kinetic, what you call, total energy becomes 0 means kinetic energy also will become 0, potential energy also will become 0. Okay, right. Okay, ma? So understood now, ma, what is meant by total energy? Now see one more point which we will discuss here. What is the potential energy of a satellite? It is minus GMM divided by R. This is the equation for potential energy, no? Are you able to understand, ma? And potential energy is also negative. What is the meaning of this? Potential energy is also negative, no? What is the meaning of this? Again, same concept. Potential energy negative indicates that satellite is bound to that particular planet. So until you make potential energy 0, this satellite cannot escape the gravitational field of that particular planet. Are you able to understand, ma? So therefore, negative potential energy indicates that satellite is under the attraction of what? Attraction of planet. Are you able to understand, ma? So therefore, if I want to make a potential energy 0, then what I have to do? Supply same amount of positive potential energy, then potential energy will become 0. And what is meant by potential energy 0? That is the maximum potential energy satellite can have. Okay, ma? What is the maximum potential energy of a satellite, ma? It is 0. Understood? Now let us try to understand this statement. Clear? See, ma. So therefore, consider this is a planet and here there is one orbit. Understood, ma? So here a satellite is present, it is revolving around this orbit. Now let us take one more orbit. Okay, ma? So radius of this orbit is R1, radius of this orbit is R. Potential energy of this orbit is PE1, potential energy of this orbit is PE2. Now can you say which orbit has highest potential energy? First orbit or second orbit? First orbit. How can you say? Distance is lesser. So therefore you are saying that potential energy is greater. But here I have negative symbol, no? Negative symbol is there, no, ma? Okay, we will do one thing. First, completed by this one. First of all, we will study without any symbol. Okay, ma? We will take magnitude. So for first orbit, potential energy PE1 is equals to, magnitude wise we will do, then it is how much, ma? It is GMM divided by R, R1. Clear, no? For second orbit, okay, ma? PE2, magnitude of PE2 is how much? GMM divided by R2. Okay. Now magnitude wise, which one is greater? Definitely PE1 is greater than PE2, no, ma? Magnitude wise. Why? Vinali. Because R1 is less than R2, no? And R1, R2, they are present in numerator or denominator? They are present in denominator. So if denominator is smaller, total value will be greater. That's all, no, ma? Denominator, if it is smaller, total value will be greater. Denominator enta chinnaga unte total value anta ekkuva untundi. Therefore, I can say magnitude of PE1 is greater than magnitude of PE2. Can I say like this? Potential energy of first orbit is greater than potential energy of second orbit. Okay. But now if I place minus symbol, now for example, let us consider this potential energy is 10 joules, this potential energy is 8 joules. Definitely 10 is greater than 8, no? 10 is greater than 8. It means that potential energy of first orbit is greater than potential energy of second orbit magnitude wise. Now what I do now, we take actual values. What is meant by actual values, ma? Now I have to place a negative symbol there. Now it will become minus 10 joules and minus 8 joules. Which one is bigger? Minus 8 is bigger. It means the potential energy of first orbit is not bigger. Potential energy of second orbit is bigger. Therefore, potential energy of second orbit is greater than potential energy of first orbit. Understood? No? Similarly, if I take one more orbit, if I take third orbit, potential energy of this one I can call it as PE3. Okay, ma? So PE1 is how much? PE1 is minus 10 joules. PE2 is how much, ma? Minus 8 joules. PE3 will be how much? Minus 6 joules, like this. Clear, no? So as the number of orbit is increasing, what is happening to potential energy? Potential energy is increasing. మీరు కోడి బ్రెయిన్స్ కాబట్టి ఇంత డీటెయిల్డ్గా చెప్తా ఉన్నాను. ఇంకా కన్ఫ్యూజ్ అవుతా ఉన్నావా? అండర్స్టూడ్ బా? సో యాజ్ యు ఆర్ మూవింగ్ అప్వర్డ్స్, magnitude wise value is decreasing. Magnitude wise value is decreasing. But negative symbol is also present, no? So if negative symbol is present, minus 6 is greater than minus 10. It means potential energy is it increasing or decreasing? Potential energy is increasing because minus is present. So it increases up to which level, can you say? It increases up to 0. Beyond that it cannot increase, no? Are you able to understand? So therefore, maximum potential energy any satellite can have is 0. Understand? And it is possible only when satellite moves out of the gravitational field of that particular planet. Field nu odili vellipoyindi anukondi. Okay ma? Then its potential energy will be 0, and that is the maximum potential energy satellite can have. Same discussion you can apply for Rutherford's model also, for Niels Bohr model also in chemistry. Are you able to understand, ma? So make it out. So therefore what I write? Therefore as orbit radius increases, potential energy also increases. Okay, ma? And the maximum potential energy a satellite can have is how much, ma? Can have is 0. Okay, so PE max is how much? 0. And when it is possible, when satellite just escapes the gravitational field of GF ante girlfriend anukundarayyo, gravitational field of planet. Understood, Nama? It means now there is no force of attraction between them. In between planet and the satellite, there is no force of attraction. If there is no force of attraction, potential energy is 0. Understood, Nama? So therefore that is planet and satellite are at infinite separation. So when they are present at infinite separation, what is the potential energy between them? 0. And that is the maximum value. 0 ante ledu ani ane kada dani artham. That is the maximum value. Understood, no? So this is a small discussion on potential energy and total energy. If you don't understand this concept carefully, problems you can never solve. Okay? So what is meant by negative energy and how it is changing with respect to orbit, and what is the maximum potential energy possible? If you don't understand these concepts carefully, problems can be never solved. Okay? That's it. Come on. Now, Sima. So escape velocity. What is meant by escape velocity? So, Sima, consider this is a planet. Okay, Sima. If I throw a stone with a particular velocity, again it will return back to Earth, no? It will return back. But if I throw with a particular velocity called escape velocity, then that particular body, again it should not return to Earth. That means it should escape the gravitational field. Gravitational attraction adu overcome chesi vellipovali. That minimum amount of velocity is nothing but escape velocity. Are you able to understand, ma? See, ma, gravitational field of a planet, there is no certain boundary. So we cannot say that it is existing only up to here. Like that we cannot draw any boundary. Are you able to understand, ma? So this is just a theoretical concept where we cannot draw the boundaries for any planet where gravitational field is ending up to here. Okay, I cannot say that the gravitational force is only up to here, beyond that there is no force. I cannot say. So just for our hypothetical calculations, we are drawing one boundary here. Understood, Nama? So therefore, if I project any body, okay, ma, with a particular velocity, then it should just escape the gravitational field. What is meant by just escaping? So its final velocity should become 0. Are you able to understand? It means just after crossing the gravitational field, how much should be its velocity? It should be 0. Okay, ma? And if final velocity is 0, kinetic energy is also 0. No? And after crossing the gravitational field, what will be the potential energy? Potential energy also will be 0, and this is the maximum value. But kinetic energy is the minimum value, but potential energy is the maximum value. Already we have studied. No? So that velocity with which I have to throw a particular body, so that after crossing the gravitational field, its final velocity, kinetic energy and potential energy should become 0. That amount of minimum velocity is called as escape velocity. Are you able to understand, ma? Okay. And escape velocity doesn't depend on direction. It is not that every time you have to throw like this only. You can throw in any direction. You can throw a body like this. Clear, Nama? Then also, if it escapes the gravitational field, then that velocity is also called as escape velocity. So if velocity is greater than escape velocity, for Earth, what is the escape velocity? Escape velocity is 11.2 kilometer per second, approximately. It means if I throw any body with this much of speed in any direction, then definitely it will cross the gravitational field. That means it will not return back to Earth. Malli Earth ki return raadu. So what happens if I throw with a velocity more than 11.2? What will happen? This is the minimum velocity. Understood, Nama? If I throw with a velocity greater than 11.2? Huh? Definitely it will escape. And after escaping also it will have some velocity, no? That is the meaning of this one, Nama. If I throw with a velocity greater than escape velocity, then even after crossing gravitational field also it will have some velocity. And with that velocity it will move continuously. Okay, so no problem if velocity is greater than escape velocity. But if velocity is less than escape velocity, again it returns back to the Earth. That is called as escape velocity. Are you able to understand, ma? So make a note of this point. So therefore, Sima, let us derive an equation of escape velocity. So I will use the law of conservation of mechanical energy only. K1 plus U1 is equals to K2 plus U2. This equation I will use. Okay, ma? So listen. Then you can write down. What is the initial kinetic energy? Half mv square, no? When it is present on the surface of the Earth. When it is present on the surface of the Earth, escape velocity is v. So what is the kinetic energy? Half mv square. When it is present on the surface of the Earth, what is the potential energy? Minus g divided by r. Because it is present on surface of Earth, no? So what is the distance from the center? R. So this is one body, this is another body. Body of small m, this is body of capital M. Then what is the equation for potential energy? Minus gmm by r. So just after escaping gravitational field, kinetic energy should become 0, no? So final kinetic energy is 0. And after just escaping gravitational field, potential energy also should be 0. Okay, ma? Therefore, what is the equation I will get? I will get half m VE square is equals to gmm divided by r. So small m will get cancelled. So therefore, VE is equals to root of 2gm divided by r. This is the equation. Are you able to understand, ma? So this is the equation for escape velocity when body is thrown from surface of the earth, because r means surface only, r means radius, where body is present on the surface of earth. If I throw with this much of velocity, then body never returns to the same planet once again. But here friction due to air we are not considering. All these are theoretical calculations. Friction due to air also will be there, no? So definitely velocity should be greater than this much. But theoretically, if there is no atmosphere, this is the velocity with which I have to throw the body. Okay, ma? And this is from where? From surface of earth. From surface of earth. Okay, ma? So if I am not throwing from surface, let us write one case. Okay, ma? For example, this is earth or any planet. I am throwing the body from here. Okay? It means already body is present at how much distance? Body is already present at a distance of r. Where r is called what? R is called r plus h. Understood, Nama? Then in that condition, just here instead of small r I have to write capital R, instead of capital R I have to write small r. అర్థమవుతుంది కదమ్మా? If I throw from the surface, then I have to use capital R. If I am already throwing from some distance above the surface of earth, then the same formula can be changed how? Escape velocity is equals to root of 2gm divided by small r. I can write like this. Okay, ma? This is in which condition? When body is thrown at a height of, from a height of h. Okay, where this small r is equals to r plus h. Are you able to understand the conditions? That's all. Make a note up to here, then we will study some more details about this one. Okay, ma? So therefore, we have written up to here, no? So if you substitute all the values already we have studied, no, ma? From surface of the earth, it is 2gm divided by capital R. Substitute all the values. So 2 into g value 6.67 into 10 power minus 11. Mass of the earth is 6 into 10 power 24. Radius of the earth is 6400 into 10 power 3 meters. If you do this calculation, then you will get 11.2 kilometer per second. That is the escape velocity of earth. Different planets have different escape velocities. For earth, this is the escape velocity. So g value changes. Mass and radius will change. G is a universal constant, it will never change. Mass and radius of the planet will change. Okay? So if I throw any body with this much of velocity in any direction, okay, ma? Then the body will escape the gravitational field of earth. Understood, no? Huh? Center of earth, again you apply law of conservation of mechanical energy. Okay, ma? But unfortunately nobody can go to the center of earth. We have to throw every satellite from surface only. Okay, so there is no manavule. We know mass of sun, no, ma? And we know radius of sun. Mass depending on size, its density, what are the gases present. No need of going nearer. Okay? చందమామను మీరు చూస్తూ ఉన్నారు, చందమామ దగ్గర పట్టుకొని చూస్తూ ఉన్నారా? కాదు కదా, దూరం నుంచి చూస్తూ ఉన్నారు. ఆ ఐడియా ఇక్కడ నుంచే క్యాల్కులేట్ చేస్తారన్నమాట. సో దట్ ఈస్ వై దీస్ పీపుల్ దే ఆర్ కాల్డ్ యాజ్ సైంటిస్ట్. మనలాంటి సుబ్బారావు సుబ్బక్కలు కాదు కదా వాళ్ళు. ఓకే, కంప్లీటెడ్ బా. ఓకే, So see, second equation we will write. Sima, there was a scientist in India called Aryabhatta, very nearly some more than 2000 years before, where nobody know about the spelling of physics also. Clear ma? So 2000 సంవత్సరాల ముందే ఇంకా ముందే ఉండేవాడు ఆయన. ఐ థింక్ హీ వాస్ ప్రెసెంట్ ఇన్ ద ఏజ్ ఆఫ్ ఋగ్వేద కాలంలో ఉండేవాడు. ఓకే, సో రాత్రి భోజనం చేసినాడు, బాగా చేసి కిళ్ళి వేసుకున్నాడో లేదో నేను చెప్తా ఉన్నా ఊరికి. కిళ్ళి వేసుకొని పోయి అట్లా పడుకోవడానికి వెళ్ళినాడు అనమాట. పడుకోవడానికి వెళ్ళి ముందు చంద్రుడిని చూసినాడు. చంద్రుడిని చూసి 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 పొద్దునయ్యే లోపల అర్త్కి చంద్రునికి డిస్టెన్స్ ఇంత ఉందని చెప్పినాడు ఆయన. అదే మరి ఆల్రెడీ చెప్పినాం కదా, మీరు నాలాంటి సుబక్కలు కాదు, సుబ్బారావులు కాదు వాళ్ళని. విషయం ఏంటంటే అది ఇప్పటికీ కరెక్టే. డిస్టెన్స్ బిట్వీన్ అర్త్ అండ్ మూన్ ఈజ్ 3.85 into 10⁵ కిలోమీటర్. అండ్ అబ్సల్యూట్లీ సేమ్ వాల్యూ హీ హ్యాస్ కోటెడ్ ఇన్ హిస్ బుక్. ఆర్యభట్టీయం అనే పుస్తకంలో అది రాసినాడు, తెలుసా. నాట్ ఓన్లీ డిస్టెన్స్ బిట్వీన్ అర్త్ అండ్ మూన్. సో ఒక బిగ్గెస్ట్ స్టార్ ఉంటుంది, మీరు ఇఫ్ యూ అబ్జర్వ్ ద స్కై దెర్ ఈస్ ఎ వెరీ బిగ్ స్టార్, అండ్ హీ క్యాల్కులేటెడ్ ద అప్రాక్సిమేట్ డిస్టెన్స్ బిట్వీన్ అర్త్ అండ్ దట్ స్టార్ ఆల్సో, అండ్ దట్ ఈస్ ఆల్సో ఆల్మోస్ట్ ఇట్ ఈస్ కరెక్ట్. మనం ఎక్కడున్నాం అర్థమైంది. నీట్ సీటులు రావడం లేదు వరకు. ఓకే, సీమా. సో V is equals to square root of 2gm divided by r. This is the equation of escape velocity, no? And already we studied that G is equals to gm divided by r square. So gm value is how much? Gr square. So take this value and substitute here. So V is equals to square root of 2 into gr square divided by r. So r and square will get cancelled. So square root of 2gr. Clear nama? So this is second equation to calculate escape velocity of Earth of any planet in terms of g value, small g, acceleration due to gravity. This is the equation in terms of universal gravitational constant, capital G. This is the equation in terms of small g. Understood nama? And all these equations we are calculating only for from the surface of Earth ma. Okay, and if you throw from a particular height, this is the equation. This you should not be confused. So every time he will not give the question only from the surface of Earth. He will give what is the escape velocity from a height of 10,000 kilometers from the surface of Earth. Then you have to use this relation. Understood no? That's it. So next, relation between orbital velocity and escape velocity. Okay ma? So what is the equation for orbital velocity ma? Orbital velocity is equals to square root of g into r, no? Or I can write as square root of g capital M divided by r. This is the equation for escape velocity, sorry, orbital velocity. What is the equation for escape velocity? Square root of 2g into r, or I can write square root of 2g capital M divided by r. These are the equations. So if you divide both of them, if you divide, then I will get relation no ma? Here I have additionally root 2 is there, here there is no root 2. Here also additionally root 2 is there, here additionally root 2 is not there. So if you divide both of them, I will get, okay ma? So escape velocity is root 2 times of orbital velocity. This is another important relation which can be asked in the examination. Okay ma? Escape velocity is root 2 times of orbital velocity. Okay? It means that if orbital velocity, if I increase its value to 41%, then same satellite, it will escape the gravitational field of the Earth. Why 41%? Because root 2 value is how much? 1.414 multiplied by V naught, no ma? Okay? It means escape velocity is how much percent bigger than orbital velocity? 41.4%. Are you able to understand? 1.414 V naught, no? So how much times it is bigger? 41.4% is bigger. Which one is bigger? Escape velocity when compared to orbital velocity. Already we have studied, Nama. What is the value of orbital velocity? Orbital velocity value is how much for Earth? For surface satellites? Orbital velocity of surface satellite For Earth is how much? It is 8.1 kilometer per second. Surface satellites, they are rotating with this much speed. Already we have studied, no? And what is escape velocity? Escape velocity from surface of Earth is how much? It is equals to 11.2 kilometer per second. So approximately 41 times bigger, no? 41% bigger. Therefore, what we write? Therefore, we write that. Okay. Therefore, we write, if orbital velocity is increased by, if orbital velocity is increased by 41%, then that satellite will escape the gravitational field of the planet. Understood, Nama? Okay. So if you increase velocity, it will go to another orbit. Velocity 41%. If V0 is increased by 41%, then satellite will escape the gravitational field of that planet.
Sir, 40 or something, sir, 1.4.
Huh? 414, Nama, 41.4. 1 into V0 means both are same. How much a fraction is bigger? 0.414 is bigger. Fraction multiplied by 100%. So 41.4%. That's it. Okay? Make a note of it. Okay, ma? So see, my next concept is geostationary satellite. Geostationary satellite means, Sima. So definition we will study afterwards. First of all, see here. So consider this is Earth. Okay, ma? And here there is one satellite. Okay? And here there is one observer. This is the observer and this is the satellite. Okay? So to this observer, this satellite is always appearing to be in rest position. You cannot see satellites, just for our understanding I am saying. Clear, Nama? So this observer, he sees in the morning, Chandetkon bathroom potune, he saw this satellite and it was right above him. Clear, Nama? Right above him means ante tala meeda undani kaadu. Somewhere he was observing. And at afternoon time he observed the satellite, still it is at the same position. In night also he observed the same satellite, still it is in the same position. So he started thinking that satellite may be in rest position, it is hanging in the air. But is it possible? It should rotate, no? Otherwise it will fall on the surface of that. So how this person is able to see this satellite in rest position? Can you say? See, Earth is rotating with some angular velocity, no? And its time period is 24 hours. Okay? So if this satellite also rotates with a time period of 24 hours, then relative angular velocity between observer and satellite will become 0, no? Okay, ma? Angular velocity of satellite with respect to observer will be 0. So therefore, when satellite's time period is also 24 hours, then to this observer, satellite appears to be in rest position. Both are moving. Okay, ma? So after some time, this observer will come up to here. He will reach to this height. He has rotated. By that time, this satellite will rotate and reach up to here. So always to this observer, satellite is in rest position. Therefore, that type of satellite we can call it as geostationary satellite. Geo means Earth. With respect to Earth, it appears as if it is in rest position. Stationary means rest, no? So with respect to Earth, this satellite appears to be in rest position. That is why it is called as geostationary satellite. So what will be its time period? Time period will be 24 hours because Earth has a time period of 24 hours. Clear, Nama? And what is the equation of time period we have written? 2 pi into square root of r cube divided by gm. This is the equation which we have written, no? So therefore, time period is how much? 24 hours. Hour means how many minutes? 60. Minute means how many seconds? 60 seconds. So this is equals to square root of r plus h whole cube divided by g into m. Okay, ma? No? 2 pi I forgot. 2 pi. 2 pi into square root of r plus h whole cube divided by gm. If you substitute all these values, then I will get height to be 36,000 kilometers. Okay, ma? We know all these values, no? R value we know, G value we know, mass of Earth we know. All values if you substitute, and for this time period, what is the height at which this satellite should rotate? This satellite is present at a height of, how much height from the surface, ma? From the surface it is at a height of 36,000 kilometers. And from the center of Earth it is present at how much distance? Here additionally R you have to calculate, no? Therefore from center of Earth, okay, ma? Satellite is at a height of, satellite is at a radius, that is better, is at a radius of how much? 36000 plus 6400 kilometers. So total how much, ma? 42,400 kilometer from center of Earth. Okay. So this satellite is called as geostationary satellite. So what is the height from the center, ma? 42,400 kilometer. From the surface 36,000 kilometer. So if satellite is present at that much height, then its time period will be 24 hours. Then always it appears to be in rest position with respect to the satellite, with respect to the observer on the Earth. Understood, no, ma? That's it. And what is its velocity? We know orbital velocity, no? Orbital velocity is square root of gm divided by r. This is the equation of orbital velocity, no? Substitute the values here. So v naught is equals to square root of g value, all we need, again we need not write all this. Then I will get orbital velocity is approximately 3.1 kilometer per second. Okay, ma? So what should be the speed of geostationary satellite? Speed should be approximately 3.1. At what height? At a height of 42,400 kilometer from the center of Earth. And for surface satellites, what is the height? What is the speed? 8.1. For surface satellites, it is 8.1. But for satellite, this is very long distance, no? So because distance is increasing, velocity is decreasing. Already we said, no? Satellites which are very close, they will be moving very fast. As the distance increases, radius increases, velocity, orbital velocity decreases. Okay? That's it. Make a note up to here. Okay, ma? So let us see the next concept, ma. Body is thrown with a velocity greater than escape velocity. Okay? What is meant by escape velocity? Already we have studied, no, ma. For example, this is a planet. Okay? So what is that velocity with which I have thrown the body such that just after crossing the gravitational field, that is just after reaching this position, final velocity should become 0. That is called as escape velocity, no? So escape velocity means minimum amount of velocity required to cross the gravitational field. It means just after crossing the gravitational field, final velocity should be how much? 0. So that is called as escape velocity. And what is the escape velocity of Earth? Escape velocity of Earth is nearly 11.2 kilometer per second. Okay, ma? So if I throw a body greater than this velocity, then what will happen? If I throw with escape velocity also, it will never return to Earth. I am asking if I throw with velocity greater than escape velocity. Escape velocity is 11.2, no? If I throw with 12 or 13, then what is going to happen? Then what happens is, even after crossing gravitational field, this body will have some velocity. That's all, no, ma? When I throw only with this velocity, then just after reaching the gravitational field end, its final velocity will become 0. But if I throw with a velocity greater than escape velocity, then even after crossing gravitational field also, body will have certain velocity. That is understandable, no? If you are giving a velocity greater than required velocity, then even after crossing gravitational field also, it will have certain velocity. So make a note of that point. So what we'll write here, if a body is thrown with a velocity, okay, ma, greater than escape velocity, Okay. Then after crossing gravitational field, body will have some velocity. Okay, ma? So how can I calculate that? Again, I can use law of conservation of mechanical energy, no, ma? Because only gravitational force is acting. Definitely we can use law of conservation of mechanical energy. What is law of conservation of mechanical energy? K1 plus U1 is equals to K2 plus U2. That's all, no? Now see. Now let us take the assumptions. So this is the planet. Okay, ma? And consider this is the end of gravitational field. See, there is no specific boundary. We cannot say gravitational field exists only up to here. We cannot say it extends up to infinity. Theoretically, we are saying that this is the end of the gravitational field. Okay, ma? So from the surface of the planet, we are throwing the body with a velocity of v, where v is greater than escape velocity. That's all, no? That's the condition which we are studying, no? Then after crossing the gravitational field also, it will have certain velocity, and let that velocity be v dash. So what is meant by v here? V is the velocity with which I have thrown. V is velocity of throwing. Okay, ma? And what is VE? B is nothing but escape velocity, the minimum velocity required. V dash is velocity after crossing what? Gravitational field. Clear, no, ma? Now we have to write a relation between them. Okay, I can use law of conservation of mechanical energy. So see, ma. So what is K1, can you say? K1 means when it is present on the surface of the planet, with what velocity I have thrown? V velocity. So what is the kinetic energy? Half m v square. Clear, no, ma? Potential energy? Potential energy 0, na? How it is 0? When it is present on the surface of the planet, it is at a distance of r, no, ma? So therefore, what is the formula for gravitational potential energy? Minus gmm divided by r. This is the formula, no? Where capital M is the mass of the planet, small m is the mass of this body, r is the radius of the planet. Minus gmm by r. So this is equals to final kinetic energy. After crossing gravitational field, what is its velocity? V dash. So kinetic energy will be half m v dash square. Final potential energy? 0. So after crossing gravitational field, satellite or body will have maximum potential energy, no, ma? Already we studied about potential energy, no? After crossing gravitational field, body will have maximum potential energy. And maximum potential energy is how much? 0. Already we have studied, no? Now this is the relation, ma. Now I am supposed to derive a relation for v dash. Okay? Now see. So we know what is the formula for escape velocity, ma? Square root of 2gm divided by r. This is the formula for escape velocity, no? Okay? So therefore VE square will be how much? VE square will be 2gm divided by r. But here I have only gm by r, no? So therefore what I will do? I will do one thing. So minus, I will multiply and divide by 2. So 2gmm divided by r is equal to half m v dash square. So if I multiply and divide by 2, nothing will happen, no, ma? There is no change. Okay? But what I will get 2gm by r, no? So this one I will get, this one. Clear, no, ma? And what is 2gm by r? V square. So substitute there. So half m v square minus, there 1 by 2 is present, multiplied by ve square multiplied by m is equal to half m v dash square. Okay? So half m will get cancelled. So therefore what I am left with? V square minus ve square is equal to v dash square. So therefore what is v dash? This is equals to square root of v square minus ve square. Okay, ma? So this is the final velocity with which body will travel after crossing the gravitational field. Okay? Gravitational field దాటిన తర్వాత కూడా దానికి ఇంత velocity ఉంటుంది. And this velocity now it is never going to change. Because there is no gravitational force of attraction, no? This velocity will never change. Okay? So after crossing gravitational field, body will continue to travel with this velocity. Understood, Dhamma? So I think in the last year or before year question, direct question was asked on this relation. Okay? So make a note. Okay, ma? So let us see this question, ma. So there is a satellite of mass m rotating around a planet of mass capital M at a radius of 2r. Okay. Now I want to make this satellite to rotate in an orbit of radius 3r. Then I have to supply some energy now, because already we have studied as number of orbit increases, energy of orbit also increases. Same concept we have studied in chemistry also, no? If you go to higher orbits, energy of electron increases. Same concept here also. If satellite goes to higher orbits, what happens to its total energy? Total energy increases. It means that initially where it was rotating, this particular satellite, for example, if this is the planet, it was rotating around this orbit. And what is the radius of this orbit? 2r. So it was rotating here. Okay, ma? So I want to send this satellite to a higher orbit, whose radius is how much? Whose radius is 3r. So I want to send this satellite from here to here. Understood, Nama? Then in that condition, definitely I need to supply energy, no? Why? Because lower orbit is always having lesser energy. Higher orbit always has greater energy. So how much energy I have to supply? That is the question. How can you say? How much? Huh? No. How you have to calculate this one? Hello. So this is second orbit, no? So calculate total energy of second orbit. Okay. Calculate total energy of first orbit. Then what is the energy I have to supply? Energy supplied is equals to total energy of second orbit minus total energy of first orbit. That's all, no? Clear now? So what is the energy present in second orbit minus U2 energy present in first orbit? The energy difference only you have to supply, no? Niels Bohr model also same concept we studied, no? What is the energy difference between two orbits or two shells? That energy difference you have to supply. Same concept here also. Okay. Now we know the formulas for total energy, no? Substitute them, do the calculation and see what is the answer. Come on. Okay, ma? So do you remember the formula for total energy? What is the formula? So minus GMM divided by 2R. This is the formula for total energy, no? So therefore, what is the total energy of first orbit? First orbit, it is present in a radius of 2r, no? So therefore, minus GMM divided by 2 into r. What is the total radius? Total radius is 2r. That's all, no? Here r means what? R means radius, no? Small r is nothing but capital R plus h. Okay? So instead of 2r, total radius is already given as 2r, no? So directly you have to substitute 2r. Are you able to understand? So minus GMM divided by 4r. This is the total energy of first orbit. Then what is the total energy of next orbit? Second orbit is equals to minus GMM divided by 2 into, now it has to go up to a radius of 3r, no? So r value is 3r. So it is minus GMM divided by 6r. So therefore energy supplied will be how much? Energy supplied should be equal to minus GMM by 6r minus of minus GMM by 4r. Okay. So therefore just do this calculation. So GMM divided by 4r minus GMM divided by 6r. Okay, ma? So take the LCM of 6 and 4. 6 2s are 12. 12 is the LCM. So 12r I can take. So therefore it is 3 GMM minus 2 GMM. Okay. So therefore it is GMM divided by 12r. So that is the amount of energy I have to supply. Then this satellite, it goes from first orbit to second orbit. That's it. Okay, ma? Now answer, I got a positive answer or negative answer? Positive answer. So what is meant by positive answer? Positive answer means we have to supply energy. That is the meaning of this one. Okay, ma? Energy is not taken from the satellite. Energy is supplied to the satellite. That is meant by positive energy. Okay. Already we studied no, negative energy means we are getting energy. Positive energy means we are supplying energy to the system. That's it. Okay. దాన్ని ఇంకొంచెం శాస్త్రీయంగా చెప్పు. Okay, ba? Now see. So there is a satellite of mass m rotating around a planet of mass m in a radius of 2r, just like previous problem. But now we are not sending the satellite to 3r. I have to send this satellite into infinity. Into infinity means what? It should escape the gravitational field. Just escape. Just escape means what? Just escaping means after escaping its velocity should become 0. Final velocity should become 0. This means just after crossing the gravitational field its velocity should become 0. That is called as just escaping. Okay. Now see. So therefore how can I calculate Sima? Total energy in an orbit of 2r, how can I calculate? Formula is minus gmm divided by r. 2r. This is the formula. And what is the radius in which it is rotating? 2r. So substitute 2r. So minus gmm divided by 2 into 2r. So how much? It is minus gmm divided by 4r. Okay. So this is the total energy of this satellite. Then what is the total energy at infinity? If it just crosses the gravitational field, total energy at infinity is nothing but a kinetic energy at infinity plus potential energy at infinity. That's all, no? That is called total energy, no? So just after crossing the gravitational field, its final velocity should become 0, no? Then only we are discussing about minimum energy. Minimum energy means already we studied, no? Just after crossing gravitational field, its velocity should become 0. It means kinetic energy is how much? 0. Potential energy is already 0. Because once it reaches the position of end of gravitational field, maximum potential energy will be there. And maximum potential energy is how much? 0. Okay, ma? So therefore, this is the total energy at infinity. 0. Okay. Therefore, energy supplied is how much? Energy supplied is equal to total energy at infinity minus total energy at first orbit or orbit. Okay. This is the method in which I have to do, no? Final energy minus initial energy if you do, then that is the energy which I have to supply. So therefore, total energy at infinity is 0. Now what is the energy in orbit? It is minus gmm divided by 4r. Okay, ma? Therefore, minus of minus will become how much, ma? Plus. So gmm divided by 4r. So this is the amount of energy I have to supply. Already we studied this one, no? So first you calculate total energy, ma. Same amount of positive energy if you supply, then total energy will become 0. Already I discussed this point, no? So if it is minus 10 joules, you have to add plus 10 joules. Minus 10 plus 10? 0. Then total energy will become 0. It means I have to supply same amount of positive energy. This is negative energy, no? Same amount of positive energy if you supply, then any body just crosses the gravitational field without any velocity. Okay. And this energy is also called binding energy also, no? What is meant by binding energy? Minimum energy required to send the satellite to infinity. That is binding energy. And what is binding energy? Just negative of total energy. N is already. So what is the relation between binding energy and total energy? Just negative of total energy. Okay. So negative of, what is the total energy initially? Minus gmm divided by 4r. So minus of minus plus. So plus gmm divided by 4r. You can do like this also. Understood, Nama? That's it.